All right, sorry about all that, guys. This is was an interesting way to start class. Um, Today is a lecture where we're going to introduce tipping points, and so I think it helps to bring it back to kind of sustainability, in that we're talking about public sector applications, and so there's more policy things and so on. So let's see how that works. Back in the PowerPoint here, maybe. All right, so the chapter starts with this back with Forrester, kind of where we began in this book with urban dynamics. And so hopefully this is becoming really familiar, this idea that, and this happens in a lot of cities. You get a period of urban growth, and then suddenly at some point in time, there is stagnation. Happens to tons and tons of cities. It's just sort of this common pattern. And so it's one of these things that we assume that because we see it across cities that are in different places and have different circumstances, that it's probably some endogenous part of being a city. It's not like, it's not being externally forced on the city. It's just some natural aspect of the development of a city. So we can form a research question then about that. And that question might have to do with, what observable processes or measurable processes might be working in concert to generate this pattern. So how do we explain this pattern? Because if we can explain it, maybe we can hold off on whenever this stagnation period began. And so that was the general idea when Forrester was at MIT. And as big universities like to do, when politicians, kind of retire from politics, they get, for some reason, hired, well, mainly for fundraising reasons and things like that, hired to join universities. And they sometimes have useful and interesting information that comes along with their experience, as was the case of the former mayor of Boston, John Collins. And so these two basically had offices down the hall from each other. They would have lunch and they would talk about this. And so they were both interested in this general pattern. And so Forrester would pick Collins's brain and they would come up with a model to try to understand urban growth. And so that's kind of what came out of that. So this is a simplified causal loop diagram of a hypothesis for what might help answer this question of what are the sort of observable processes that explain urban growth and stagnation. So the idea is we start with this sort of thing. We're going to build a sim. We're going to see if the sim can reproduce these patterns. And if it can reproduce the patterns, then we can drill down into the sim as if it was a microscope where we would look at the layers of a city that are harder to see when we're just looking at the city at the normal time scale. So what did this kind of hypothesis look like? So this possible answer to this question. And, because growth was central to it, it kind of makes sense that Forrester started with a growth loop. And they said, well, where is the key thing that's causing the city to grow? And they focused on infrastructure. So the idea here was that if you have an expansion of infrastructure, after a little bit of time, it will turn into new infrastructure. And that new infrastructure will possibly generate returns to the city, which will allow them to invest in more infrastructure. So you build a road, you get more commerce, you have more money to build more roads. But it takes a time to do that building there. So, all other, if we think about just this seems like a city could grow forever. So then we can think about, well, what are the things that might limit this? So, well, this is a physical thing like infrastructure. It exists in free space. So, maybe space is a limiting factor. So they throw in some other things. They say, well, when you get more infrastructure, that increases your total infrastructure, great. But that also increases the total amount of land, the footprint of your city. And ultimately, that's going to cause you to reduce. It's going to make it harder and harder for you to further expand your infrastructure because there's just less land left over. So that's why they sort of called this the land limiting loop. And you think about it, is it only land? Well, then so they started to brainstorm and so what other things can limit growth? Well, that new infrastructure, not only it generates growth, great, but as it gets older, it stops being that generative. So that new infrastructure, while it's sitting there, after some time, another one of those delays, it becomes old infrastructure. And that old infrastructure, as we'll see, is not going to be as beneficial to the city. So this new economic infrastructure, that is what's driving the new economic returns, allows you to do more investment. But as it becomes old infrastructure, it's not helping to generate those returns that are hidden over here, that helps you further expand the city. So as things age out, they just kind of take up space without having a lot of return. So that's one hypothetical thing that could be going on here. But that old infrastructure still contributes to total infrastructure. So, with more old infrastructure, you still have a land limit. So this whole thing, I mean, he's got this sort of aging and land limit, and we could kind of argue about whether, this is a new limiting loop, but definitely this aging loop is really important for this balancing process. So all the bottom here are really about space. So you can, with more prosperity, you can generate more cool stuff in a city, which generates more prosperity, but eventually the cool stuff you build becomes kind of old and busted stuff that doesn't help you with more prosperity. So this is all kind of a space hypothesis. So then you go to your expert, your mayor, and you say, what other bad things happen over time that help, that might reduce a city's growth? So this is all the land stuff. And that comes up to this stuff up here, which is more people stuff. And so if we think about it, the arrows here, this is the new infrastructure, makes the city more attractive, but the old stuff makes it less attractive. And the attraction of a city is what draws people into it. So when a city is attractive, then relative to nearby cities, eventually people say, hey, it really seems like this town is a lot nicer than it used to be. Maybe I should move into there. So I've got my alternate cities, my perceived relative. And so that causes people to move into the city. But over time, that increases the urban population, and there should be a minus here. And I really thought there was a minus here, so I don't know where it went. That's going to end up decreasing the city's attractiveness. And so this is a little bit like, a balancing loop with delay, where effectively what's happening here is the water level is the city's attractiveness ends up becoming very similar to the attractiveness of cities next to it. So all cities eventually start, really attractive relative to those around them. But as more people move in, it gets denser, and then they end up coming down to sort of a background level of attractiveness where you get no net migration. And that's what's happening here, is that eventually you get zero net inward migration. And with less people coming into a city, then that'll be, again, less prosperity, because you will have less kind of activity going on in the city. So we have these kind of two things going on. We've got kind of space limits in a city, but also density issues. And those might be two things that explain why you get initial rapid growth and then a bunch of these balancing loops kind of fighting against it to level it off. So that was kind of their basic idea. They said, well, how do we implement this stuff? So that'll be kind of the next step. So these are possible processes. So this is kind of like the thought process of building a complex model, like in your final projects. So we started with a question. We had sort of a dynamic hypothesis. So the question was sort of, what's generating these common patterns? Here's a hypothesis. Maybe it's this stuff. Well, okay, if that's true, we need to test to see if this generates a similar pattern. Well, we're going to need to build a simulation model to generate a prediction and then test the prediction, the output of the simulation model, against reality to see if our hypothesis holds up. So that's what we're going to do. So behind the scenes, we need to build a stock and flow model. So we think about how are we going to implement this causal loop diagram as a stock and flow model. And so that's what they go in here. And this looks complicated. We're going to zoom in on every row here. And it's all the same stuff you've seen before in tiny little models that we've kind of gone over. So like this top row is industry. This one's housing. This one's population. Let's look at industry. This basically is like an SIR model. It's an age-structured population model, like we've seen in a lot of these things. What they're basically saying is there's some rate of new construction that generates new enterprises, and then there's some rate of aging, which then turns the new enterprises into mature businesses. But then those mature businesses age into declining industries, and then eventually those industries get out of the way and they make room for new enterprises again through demolition. So it's a little bit like births, SIR deaths, or something along those lines. So this is a very similar model. So we're thinking about, you should, like, when we think about the city, we think that there are these groups that have been around for a long time, not so long, and just came out. And in your head, you could think, I can bin my population into those three groups and model how you flow from one group to another. And you think that's just like the SIR model, where if I bin my population and an S and an I and an R, and we know that everybody's eventually going to be recovered, and they'll be infectious in between, and they'll all start out susceptible. And but then I kind of erase the SI and R, and I put different names up it, and it's the same dynamical properties. So I can build off of what I already know. Now, that's industry great. I kind of have all that. I'm not going to worry about the connecting networks right now, the coordinated networks. Now, housing. We do a very similar thing, just a little bit more complexity. So housing, there's a similar age structure thing. All houses start premium, and then they age into being worker housing. So they get a little that maybe rent goes down and so on. And then they become maybe underemployed housing. So rent goes really down, they're less attractive. Now, we can't just have all housing start with premium. So this starts out looking like an SIR type model, but we need sort of a birth rate of this intermediate one. So we need to start with some worker housing and have worker housing always be generated at some background rate. And that's all they've done here with another inflow. So you're gonna have two inflows going to one stock. So some of you I've been seeing on your projects, when we did our check-ins, you had one inflow because most of the models I've shown you only had one inflow, and you had complex expressions in the inflow, but where some of them had a plus. Wherever you have a plus inside an inflow, you can ask yourself, is it actually going to be easier for me if I actually just split the thing on the left and the right of the plus sign and put the left one in here and then draw a second inflow and put the right one in there? Because if you put a plus inside an inflow, that's the same thing as just creating another inflow. And so that's kind of what we're doing here. And it just makes it clear what's going on. And then similarly, the underemployed housing, there's going to be underemployed housing constructed without going through this process, and that's what they've added there. So it's just basically like one of these age structured models, just with extra birth rates kind of coming in. So not that different. Things get a little more complicated when we think about the population, but if you kind of squint, it looks just like the other two that we just looked at. Again, if we got to look through here, we've got so if I kind of think in the other direction, we've got underemployed arrivals. So people arrive to the city and they don't have a job. And so nominally speaking, they eventually get a job. They become workers. And then nominally speaking, they stay in that job and they eventually become management. And that's the sort of nominal pathway. But in reality, we know that doesn't always work out exactly that way. And so along with the kind of SIR age structured model, going from right to left this time, we also need maybe a transition from worker back to unemployed. Some workers lose their jobs and have to find new jobs. And so there's a bidirectional flow here. But we may not in this city want to direct, we might assume that people, once they get into management, they manage to hold on to their jobs or a management position from that point on. So there's no bidirectional flow there. Likewise, we add a little bit more complexity in that people can come in as underemployed. Maybe they call them births here. So I don't know if births is necessarily the right term. You can think of other processes. I mean, people aren't born into management. Maybe some are. I don't know. But we've got an inflow directly into each one of these bins. But then likewise, some workers, they're going to go to other cities. So we got a departure rate, and they're going to come from other cities, an arrival rate. And some underemployed, if they're underemployed for long enough, they will also depart the city themselves. And likewise, managers might come into the city. So, it's got it looks complicated because there's all these flows and everything, but just try not to worry about the flows. Always focus on the stocks. And then the flows are just how you get from stock to stock. And this is just a normal age structured population model where we cut the population up in threes, but there's just a lot more ways to get into a bin or out of a bin. And that's all that's there. So are there any questions about this structure here? We had 9 different stocks, pretty complex model. We haven't talked about the coordinating network or anything. A ton of flows. But I hope when you look at this, you can sort of see that it's not that complicated when I actually look down into it, when I drill down into these 9 stocks. Questions here or online? Okay, so once you've got the stocks and the flows, then you start worrying about the coordinating network. And that can get uglier. So this is just a subset of all of the coordinating the links that come in. I'm not going to go over all this sort of stuff. All I'm focusing on here is like in the caption here, these are the information links to underemployed arrivals. So we have to figure out like what drives underemployed arrivals. Why do people come into the city without a job, you know, in the hopes to get a new job? And we can sort of see here that there's a bunch of like, you know, there's the number of underemployed people might matter, the amount of housing might matter, what type of housing might matter, what type of businesses around might matter. So you end up, you know, summing all these things together, and it might seem like there's just a lot of parameters to fix, and there are, but in theory, you could go to an economist and ask them, like, for a particular city, as you grow the number of new enterprises, what's the inflow rate, the change in inflow rate that you see from new people coming into the city? And they could give you those correlation coefficients, and then you could implement that. So if you talk to statisticians, you talk to economists, they can help you fit these parameters. It's important to just sort of come up with, hypothetically speaking, if you had the parameters, what would they be? You're not going to have a model this complex. Again, this is just modeling sort of one of these variables and all the links that come into it. All the other sort of variables, you know, there's they're going to have a similar mess of things coming into them. And your model for your final project won't be this complex, but it's a similar idea where you're going to be able to find information for some of these things, but for some of them, you're just going to have to make up for the purpose of this project and give me kind of a justification. We couldn't find any data on this, but you know, reason through it. We assumed based on experience in Phoenix that it's this. And you could say, and if you're not really certain, run your model with several different variables, like run it with twice as much, with half as much, and see if the predictions change much. If they don't change much, say that. Yeah, we weren't sure, you know, we did not have information about this parameter, so we tried a threefold, you know, range of these parameters and got very little difference. Or if there is a big difference, then tell me that. Say we tried a threefold, you know, change in this parameter, and we got, you know, these different regimes where, you know, it was better to be X under certain regimes, and better to be Y under certain regimes, and then that tells me that an important next step, not for you, but for somebody else, is to figure out what this parameter is. And that's fine. So you don't need to know every parameter for your final projects, because it's really hard to do. So we started with a relatively simple causal loop diagram, capturing the salient features of our idea. We drilled down and built a simulation that's consistent with this, but has a lot more details. And our next step is then to run that simulation. And it basically is just unrolling the ideas that are captured in the causal loop diagram that we started with. So any questions about this so far before we look at the validation, the actual execution? Okay, so you run the thing and you can plot a lot of these stocks, you know, and so like they've got, you know, premium housing down here, new enterprise, and so on. And the first thing we notice, I hope you notice, is that it has kind of the right shape. You know, it has the growth and the stagnation. So it, at least it passes the sort of face validity. It seems to match kind of what we're expecting. But on top of that, then it allows us to sort of think more about what's really important here. Like we see that a leading indicator seems to be labor and worker housing. So it seems like you get a tapering off of labor right after a tapering off of worker housing, and everything else kind of follows after that. So I might not know how to kind of order things, but in this sort of generic city that I've built, then it sort of suggests that the kind of limiting factor for growth is probably labor and worker housing. And so if I want to think of what to invest in, it's kind of like almost like, you know, supply side versus demand driven type of thing. Like, do I want to bring in a lot of big businesses, or do I want to make sure the workers have got places to live and all that? And this suggests that, well, the the stagnation starts when the workers maybe can't find housing, and so they then start leaving. So maybe worker housing is the more important investment. And that's something that I can kind of take from this. And that would be great. If you had a qualitative result like that in your final projects, you generate one of these things, you say, here's a pattern that we're trying to explain. We build a model that has that pattern, and we're trying to figure out what goes into that pattern. And when we run it, we can plot 4 different stocks that we have. And it turns out that for a bunch of parameters that we tried, it's always the case that this particular stock ends up showing signs of the future, whatever the pattern is, before everything else. So maybe that indicates that that stock is driving the system. So it just gives us another way. Now, we don't know that for sure. There could be other things going on here, but it's just like looking through the microscope. Like, you may not understand what's causing a particular macro scale phenomenon, but when you look through the microscope and you notice that you can get predictors of it from these small things that you weren't necessarily expecting, then it helps you focus your efforts. So that's what I take from this behavior over time, from this BOT. So any questions or comments about that? Is that a pretty clear message for this urban growth model? It's a pretty cool looking graph too. So that's kind of nice. Okay. So yeah, that's all I'm kind of saying here. Realistic parameters generate similar things. That's what we call validation. The scales are even similar in terms of population here, population there. I'm not expecting your scales to match up in your final project. That takes like a really detailed model and really, really close parameters. But it does sort of help us get a better perspective, a generalizable perspective on things. So this whole thing was meant to sort of demonstrate, at least for me, I highlight this, because it shows that we can start with a dynamic hypothesis, and from that hypothesis, choose some stocks and flows, bring those together, generate a coordinating network where the choice of our coordinating network formulas is consistent with the causal links from our dynamic hypothesis. And then from there, generate a prediction by, so test it. So we compare simulation output to reality. So the prediction is the simulation output, compare that to reality. And if they're totally different, then that means that I probably don't know how a city works. I need to go back and figure out a new model of the city that actually matches. If they're very similar, then that means that maybe I can use my toy city as a way to better understand city dynamics in general. So questions about that message? Is that clear? Hopefully give you some food for thought about your final projects, where your final projects would be a much simplified version of this. Like, I'm expecting most final projects have 3 or 4 stocks, not 9 or whatever. Okay. All right, so now on the road to tipping points, which is definitely you probably heard about tipping points in other classes. I want to show you the kind of dynamical side of tipping points, where they come out of these models. And fisheries are a great model system for talking about tipping points. So this section here, I don't remember if Morecroft focused on tipping points specifically, but the dynamics are all there. So fishing dynamics from regulatory process. We've been looking at this fishery, since the beginning of the class. We know that the fishery has this kind of S-shaped growth pattern where this net regeneration curve is a lookup table, which hopefully we're all kind of feeling more comfortable with lookup tables, where based on the density, you either get a positive relationship with the density or a negative relationship. And when the regeneration rises with density, then it has a reinforcing feedback. When it falls, so when density gets higher and the regeneration goes low, it has a balancing feedback. And that is what generates this S-shaped growth curve in the fishery. And so that's just kind of being diagrammed here, is that if I start out at a high density, if I fish the fishery, I'm going to reduce the density, which will raise the regeneration rate. And that on this side of the curve is really great for the fishery, because that means that the more fishing you do, the more fish are produced by the fishery, which allows for even more fishing. So fishing leads to even better conditions for more fishing. The irony here is that the balancing feedback, which sets this up in the fishery, sets up a vicious cycle for the fishing process. So the fish are sitting in their balancing side, but they end up sort of leading to this positive feedback, or a vicious cycle, that it's welcoming more and more people into fish, because the more you fish, the more fish are produced. So the problem is that eventually that leads to the other side of the graph, where if you fish more, then the regeneration rate stops increasing and it starts decreasing. And so at that point, you've now fished more, and you've had experience with this in the recent homework, where as it fishes more, the regeneration rate crashes. And so if you're still fishing at a high rate, they're not being replenished. In fact, they're being replenished at even a lower rate, which is going to cause more and more fish to leave the fishery. So slight overfishing today, going a little bit from this density to this density, leads to massive overfishing tomorrow. So here, if they used to be producing up here, if you just keep fishing at this rate, then you're just basically taking money out of the principal account and your savings account, and eventually it's just going to hit zero. So there's a critical point here, and it's an example of something we're going to call a tipping point. And so it's where the dynamical characteristics of the system fundamentally change. So behaviors of the system, or states of the system that used to be stable, are unstable on the other side of this tipping point. And so we're going to try to quantify what we mean by that here. So we're going to think about, so this is our harvested fishery. So this is the same system that you, again, experimented with in your model. And so this is our behavior over time plot here. So this is just marching through the process that I was just talking about. So as a reminder, this is our fish stock. It starts up here at its initial conditions. So you've all now simulated this. So you should be familiar with this curve that you're going to see up here. And down here, we've got the new fish per year, which is this slowly rising curve. We've got the catch, which is this jump up curve here, and the ships at sea. So as the number of ships at sea jumps up, the catch jumps up. And when the catch jumps up, that's what causes the stock to decrease. But as the stock decreases, the regeneration rate increases. And when these two match down here, then inflows balance outflows. And that's the reason why we get this sustainable outcome out here, where the fish kind of level off at a sustainable outcome. So that's what we mean by a sustainable outcome. Inflows are matched to outflows, catch is equal to new fish per year, and the stock levels out and stays constant. Now, because this was a successful policy, so this number of ships seemed to be okay, then exogenously, someone might decide to increase the number of ships even more. So that's what we've got here. You increase the number of ships, which increases the catch rate. That will decrease the fish stock even more. As you decrease the fish stock, you increase the regeneration rate. And again, sustainable outcome. So it seems like you can keep adding boats and everything will be fine. But eventually what happens is that you're going to increase, like I was saying before, and this is just, again, me walking through this, and so I guess I probably could have just jumped ahead. So this is that same process where as the fish density is getting lower and lower, the regeneration rate's getting higher, you reach the highest regeneration rate possible. And after that, if you lower the fish density any further, then you don't have a sustainable outcome. So when the catch rate is higher than the max regeneration rate, the only way the density can go is down. And when it goes down, its regeneration rate also goes down, and it's going to make it worse and worse and worse. So when the catch rate is greater than the regeneration rate, fish are not replaced, fish density declines, regeneration rate gets lower, makes the problem even worse, the decline's even faster and faster and faster. So long as the catch rate stays up here, then there's no feedback that will end up causing the regeneration rate to come back to it. It's above any possible regeneration rate in the fishery. And so that could lead to extinction. Now, what's interesting is that when the density gets this low, it provides a regeneration rate which is lower than the regeneration rate that we started with. And so if we move our ships back to where we started, it doesn't rescue things. That's going to be the key point of a tipping point. We started with the number of ships that were pulling this much fish out of the fishery per year. And that number of ships was fine. But then we overfished. And after overfishing, we effectively changed the system. So now if we try to bring the ships back to this level where they were pulling out how much they were when things were fine, it's now still bad because the density is so low that these fish can't keep up with that. And so they'll continue to decline. So that's what's going to be fundamental that's going over a tipping point. Things that used to work fail to work anymore. And so you end up getting this kind of extinction. And so in a fishery example, the tipping point corresponds to something we call maximum sustainable yield, or MSY. And so the maximum sustainable yield basically is the maximum biomass that can be removed from a renewable resource sustainably. So we know that if we left the resource alone, they would be at carrying capacity. The more we fish, then we're effectively changing the steady state value of how much fish is in the fishery. And this is how much we can remove total. If we remove any more than that, we move into this dangerous zone where it's not sustainable to fish there anymore. So in other words, the things to the left of this point are like the principal in a banking account. The things to the right of this are the interest. You can only spend your interest. And so the maximum sustainable yield are kind of like the amount of money you can take out per year before you start spending all your interest. And so that's kind of what's being corresponding here. In roughly speaking, the maximum sustainable yield is half the carrying capacity. Because roughly speaking, these net regeneration curves are pretty much hump-shaped. This is asymmetric because it's a little bit more realistic. But if you imagine sort of a hypothetical version, like a mathematical version that's perfectly hump-shaped, then this maximum sustainable yield would be right in the middle. So they're always roughly about half the carrying capacity. That's the most biomass you can take out of a renewable resource before it's unsustainable. So that's a good term to know, maximum sustainable yield. It's the most you can take out of a renewable resource that ensures that it can keep regenerating. So that on our graph here, on our time series, we hit that maximum catch rate right here at this point here. So basically, when we raise our number of ships to this point, it raises the catch rate to this point, which brings the fish down, and they eventually hit their maximum regeneration rate at this point here. That's the maximum catch rate that is sustainable. Or in other words, this amount of fish that we've removed from the fishery at steady state, that's our maximum sustainable yield. So when we reach that point, it's impossible for the rise in regeneration rate to keep up, so it plummets. And so the difference between the catch rate and the regeneration rate just gets greater and greater and greater. And so the fish stock accelerates in how quickly it falls. And then you try to rescue it. And you try to rescue by bringing the ships back down to where they used to be fine. But because we're now in a different regime, things that used to be sustainable, things that used to be stable, it used to be totally fine to have this many ships and this catch rate. It's not. And you get extinction of all the fish because we crossed the tipping point. So a tipping point, as we'll see here in a second, a little bit more abstractly, is a point where the system fundamentally changes, where in order to rescue the system, you're actually going to have to do sort of extraordinary measures beyond which anything that used to be acceptable. So you might have to stop fishing for a long amount of time in order to rescue the fishery. So it's just like your savings account. Like once you start borrowing from principal, you can't just stop and then expect to be fine again. You might have to leave that savings account alone for a long amount of time before you can start taking the interest out. So we can't rescue sustainability for this thing here. So before I get kind of more abstract, I want to make sure, does this specific example, I see a question in the chat here, does this specific example make sense? Are there any questions about this, or anybody not following all these lines around here? in the story that happened here. There's a question online which has to do with how you rescue it, and the question is how to rebuild the stock. And I think I just sort of talked about that, is that you can bring the number of ships down to 0 and the stock will regrow again. But the point is, you now have to wait for the density to go back over the tipping point. So the point here is that if you start on one side of the tipping point, if you ever cross to the other side of the tipping point, you may reach a point where you'll actually have to reduce your exploitation to less than originally was, just in an effort to regrow the renewable resource back to this side of the tipping point so that you can then go back to normal. So there will be some transient period where you have to regrow this, and that might take years. So that's why it's really dangerous to cross tipping points, because if it's reversible, and we'll see in a second that it doesn't always have to be reversible, the process of getting you back to where you started might be really costly. And you might just have to give up on this renewable resource. It might be gone. I mean, aquifers are an example. They technically are renewable, but if you go over sort of a tipping point there, then it's effectively just a big empty hole in the ground. So, all right, so this tipping point in this case corresponded to this maximum regeneration rate, which we hit at this particular time here. That was our maximum regeneration rate. So the system responds differently to the same inputs before and after the tipping point. That's going to be the fundamental thing in tipping points. Your system acts like a different system after you've crossed it. So want to kind of give us a more abstract view of that. But does this make sense for the fishery? That we pushed the system so that we moved them to the wrong side of the regeneration curve. Because of that, we were stuck having to remove our boats completely to regenerate, to get them back on the other side, to grow our savings account so that the interest could be, we could survive on using the interest again. If you have $1 million in your savings account, you can probably live off the interest. But if you splurge too much, so now you only got $100 in the savings account, you cannot go back to spending, to counting on the interest for $1 million. You're gonna have to wait a long time for the $100 to grow to $1 million again. And that's what happened with the fish. Okay, so let's think about, how do we concisely, let's now move away from fish and think about general systems. And how do we sort of concisely summarize the relationship between system parameters like number of boats and long-term outcomes. And that's using something called a bifurcation diagram. So in dynamical systems models, we often summarize things like tipping points using this diagram. And this diagram, in this case, linking back to the fish, but just using the fish as a model, I'm putting harvest rate as a parameter here. So you can also think of that as number of ships, because that's related to harvest rate. So harvest rate is on this axis, and the fish population's on this axis. And so for every point here, this is going to be where does the fish population go at steady state after you allow the transients to die out. So what do I mean by that? Well, if I think about, so this is all I'm saying here. If I think about the regeneration curve, so this regeneration curve here, if I talk about this harvest rate on the y-axis, so the number of ships that correspond to pulling this many fish out per year, there are 2 fish densities that perfectly balance that harvest rate, right? So one of them is at a low density and the other one's at a high density. So if I know exactly what the density is, then I can tune my harvest rate so that things are stable. So the fish don't climb, they don't get any more fish, don't get any less fish. But I have to perfectly balance them in order to keep things exactly here. Now there's these 2 densities are fundamentally different. So we're going to call these equilibria. So if I happen to know my harvest rates here, there are 2 possible equilibria where the system can sit and perfectly be balanced, where inflow is equal to outflow. Now, in this lower equilibria, this lower density one, if you add 1 fish, the regeneration rate is going to go up. And now the regeneration rate is going to be higher than the harvest rate. And so the fish population will keep growing. So if you add 1 fish to this equilibria, eventually you'll land at the other equilibria. If you take one fish away from this equilibria, then now the regeneration rate is going to be less than the harvest rate. And so the fish population is going to continue to decline. So if you take one fish away from this equilibria, it's going to move down to extinction. And extinction actually, that ends up, showing us there's a sort of a hidden equilibria here. Once all the fish are gone, nothing can change. That stock is dead because that stock's birth rate depends upon the stock itself. So there's kind of a hidden third extinction equilibria that we call here. And if I added one fish to this extinction equilibria, it would just come back because the harvest rate is going to be so high. So, so this kind of you got to get stuck in this equilibria. But what I'm trying to get to the point here is for this one, if you bump it at all, add one fish, take one fish away, you run away from that equilibria. So that equilibria is what we're going to call unstable. So if you perfectly balance it, it'll stay there. It's like this pointer. It's got a flat bottom, so if I can stand it there and it stays up. But if I bump it a little bit, it's going to tip. And I don't want to use the word tip because this isn't related to tipping points. But it's but the idea here, it's the same idea. It's like a pendulum that is standing the wrong side up. It can balance its way, but if you bump it a little bit, it's going to flip around and go to the other position. Now the other equilibria, it's a different story. This one here is at a higher density. If you add one fish, the regeneration rate goes, so if you add one fish and we're going this direction, the regeneration rate goes down. And that means that the number of fish is going to be reduced if you stay at this harvest rate. If you remove one fish, the regeneration rate is going to go up. And so that one fish that got removed will be replaced. So if you're sitting at this equilibria, at this harvest rate, if you perturb it a little bit by adding one fish or taking one fish away, it'll come back. So we're going to refer to this equilibria as stable, this equilibria as unstable, and the extinction equilibria we also refer to as stable. That just means that if you perturb them, they're going to go out of balance. So, and that's what I'm saying here. We can take all three of those, stable, unstable, stable, for this harvest rate, and we can plot them all on this graph here. So for this harvest rate, we're going to put all three of those. And that's going to say, for this harvest rate, these are the possible long-term behaviors of this system. So that's what I'm just going to do here. And so we've got, for this harvest rate, there's the extinction equilibrium, there's the unstable one there, and there's the stable one. And if I do this exercise for this whole harvest rate graph, like for harvest rates from 0 all the way up to whatever this is, 600, then I'm going to get this curve. I'm basically going to take this curve here, and if I kind of go back and animate that, I'm basically just taking this and flipping it over so that it lives as this curve over here. So this, this curve here, it looks like a sideways version of the regeneration curve, and that's not an accident for this system. And so for every harvest rate, if I just draw a vertical line up, I can find every equilibrium. I can see that for this harvest rate, extinction is stable, this density is unstable, and this density is stable. So I get a ridge of unstable equilibria that you can't stay at, a ridge of stable equilibria, and a ridge of extinction equilibria. If this was a hill, then it's like this is the top of a mountain, and this is a valley, and this is a valley. So if you were a ball at the top of that mountain, you could sit right on the ridge. But if I just hit you one direction or another, then you would either roll down to extinction and sit in that valley, or you'd roll down to this valley and sit there. So this is like a topographical map, where this is the ridge of a mountain, and this is a valley, and this is a valley. And that's what we're kind of looking at here. And so taking away some of those lines, that's kind of what we've plotted here. So this is what we call a bifurcation diagram. One parameter down here simultaneously shows, as you change that parameter, how does the long-term behavior of the system change? And we can see that for some harvest rates, there are 3 equilibria. But for a high enough harvest rate, so when harvest rates get way up here, the only equilibria of the system is extinction. So that's what we mean by overfishing. So you might temporarily be able to harvest at this rate, but it ain't going to last. the long-term behavior of the system, the only option is extinction. So we want to make sure we're harvesting in just this region here, but depending on where we start, we might be closer to the extinction equilibria than the stable exploitation equilibria. So we also have to be careful about that. So oftentimes we're going to add to these bifurcation diagrams a little bit more kind of information, or at least we're going to kind of conceptualize them in kind of a different way here. So if I'm looking at this type of bifurcation diagram, what this is telling me is if I start in this region. So what do I mean by start in this region? If my fish density is at a particular point and my harvest rate is a particular point. So if I were to, where my laser pointer is, that is a particular fish population, a particular density, and a particular harvest rate, a particular number of ships. If I start anywhere in here, it will rush away from the mountaintop toward the valley, and this will be the stable exploitation valley. It'll sit here at a fish density which is non-zero. If I start above that, so the fish population's at carrying capacity, then for any one of these harvest rates, it will rush down to one of these stable things. So that's good, but that's only if I start in this region. If I start in any of the rest of this region, I'll lead to extinction. So this is saying that under here, these are densities. So for this, if this density is this low, if I harvest at any rate higher than this rate here, so if this is my fish density here, if I harvest at any rate to the right of this red dot, then the long term, I'm going to go to extinction. So that's the way I read this, is that this bifurcation diagram tells me how to mix my exploitation rate with my density to understand the long-term dynamics of the system. And so we can start looking at sort of, more complex pictures here where we've got this blue sustainable region and this red unsustainable region. And we can think of like long-term dynamics when we're talking about making choices about harvest rate. So what I mean by that is like, so if I put, this is our tipping point. So if I start, let's say here, so I'm sitting here at this harvest rate with this number of ships, I'm happily sitting at this population, I might want to increase my harvest rate. So I increase my harvest rate to this amount. Well, that's in this unstable region. So that's telling me the long-term behavior of my system is going to be going toward this, this extinction equilibrium. So I now have moved down toward extinction. So I recognize that, so I reduce my harvest rate back to where it was. But because I'm now in this unstable region, it's like I'm working with a totally different system. And so that's not going to work. It's going to keep rushing towards extinction. The only way I can save my system is by moving my harvest rate until this blue region way over here. And finally, I'm in the blue region, which means finally I'll get pulled back up to this valley or roll back down to this valley. And at that point, then the system will kind of take care of itself. And so once I'm up here, I'll now stabilize a very high fish population. So now that I'm way up here, it's safe for me to re-increase my harvest rate to this point, and things will come back down to where I started. So, this pattern here with this type of bifurcation, it has what we call hysteresis. And what that means is we can have a small change in harvest rate will then require, in order to us to get back, we might need to make a large change in harvest rate to get back. So hysteresis basically is history dependence. So, I mean, this happens when people like put on jackets for the cold or whatever. Like, so going into the winter, you might be less likely to put on a jacket. You're going to tough it out. But so there'll be a particular temperature that you start putting on jackets. But then coming out of the winter, there'll be a different temperature where you start taking off your jacket. And so, you know, if everything was rational or whatever, and it didn't depend on history, there would be a critical temperature, it'd be jackets on, jackets off, all of that temperature. But in reality, you have a temperature for taking off a jacket and a temperature for putting on a jacket, and they're different. And it's a similar idea here. There is a harvest rate that was sort of sustainable, and you had a small increase in harvest rate. And so you might think that a small change will end up fixing it. But if you're in this region, a small change puts you in this region, where the only way to get back into the blue is through a large change coming back. So where you are affects how you choose these harvest rates. And that's what we refer to as hysteresis. When the relationship between a parameter and the state of the system depends on the history of a system. And so these bifurcations, like this one, that have this particular shape, generate this hysteresis. And they make tipping points just so scary, because crossing them may mean that, like, it doesn't seem like it's that big of a deal to cross it, but then once you cross it, like, it may be a huge investment to get back into the blue. Yeah. Oh, like in the previous slide, like back when it was up here. Oh no. So well, that's an excellent question. So this I wouldn't call a bifurcation diagram because it's not plotting the same things. This is like a lookup table plotting the relationship at any instant of time between fish density and net regeneration. I wouldn't ask you that. I would more ask you, like, in a multiple choice or something, like, what type of diagram represents the relationship between a parameter and the long-term behavior of a system. And that's a bifurcation diagram. So the parameter here is the harvest rate. That's what we can control. And the stock is fish population. So these are different equilibria of the fish stock. And it just so happens for this simple system that net regeneration curve pretty much draws the bifurcation diagram. But for complex systems, there may not be a simple relationship. So, like, in general, if I forget about that curve up there, the way I would generate this, if I have a really complex system like that city system that we just showed, I would pick a parameter like something to do with investment in worker housing or something like that. And I would put that on this axis. And then I would choose a small value for that. And then I would choose different initial conditions for, or what if I already have a lot of, no people in worker housing, a little bit of people in worker housing, a lot of people in worker housing. And over those 3 or 4 conditions, or maybe 10 conditions, I would run for this one parameter. And I would see, how many different steady states do I get out? Like like that thing settled down at a particular level. Where did it settle down? And then I would just graph those things out. So numerically, I could walk through this parameter and I could change all my initial conditions. And if I do enough initial conditions, enough parameters, then just by running my sim, I can generate an approximation of this thing. I generated it here by looking analytically at that regeneration curve. But you can generate them, what we say numerically, just by running the sims for different sliders. Think of this as a slider. So you could have a slider down here and then adjust your initial conditions of your stocks. So this would be a stock's initial condition here. So for all these different initial conditions, you run the sim with different slider values and you see where things settle out at the end, like after 100 years. And then you plot those things in this region. And that summarizes how the thing on your slider relates to the initial conditions in long time. And that's a bifurcation diagram. So this is not, think of this as steady state values. These are like the things on the right-hand side of the behavior over time after 100 years. So it's not like what happens right after you hit play. Okay. And this point here is what we refer to as the tipping point. So a tipping point is a value of the parameter which causes you to go over, it causes the system to bifurcate. It causes the shape of the equilibria to change. So to the left of the tipping point, there's 3 equilibria. To the right of the tipping point, there's 1 equilibria. And so there's a qualitative change in the number of equilibria, and that's what makes it a tipping point. And that's the scary thing is that once you move into this different region, the system behaves differently. You might not know how to control this system, and it may require significant effort to get back to the system that you're used to. All right. So any other questions about that? I'll animate back through here. hysteresis. All right, so where does this term come from, tipping points? I'm using an analogy of a refrigerator because it's big and heavy, but we'll see in a second, it's actually a wine glass. It's kind of more common, but the idea here is you have a refrigerator, it's sitting on a platform, it's stable. In other words, I could tip the refrigerator, I could push on it, and as long as I don't push really hard, it's gonna stay upright. So if I nudge it a little bit, it'll stay upright. Now, if I put it on a platform that's tilted a little bit, the tilt of this platform, that's the parameter. And so if I put it on this platform, it's tilted a little bit. Now, if I push it, it's still not going to tip, very easily. It'll pretty much stay upright if I just nudge it a little bit. I keep doing this game, and eventually I'm going to hit a special angle. And mechanically, that's going to be the point where the center of mass of the refrigerator happens to be over the corner of the refrigerator. It will sit there, but if you happen to nudge it just a little bit, then it's going to flip over. And it's going to sit here. It's going to be perfectly happy to sit in that position. And so I would say, okay, shoot, I need to fix the refrigerator. Let me just put a level platform, sorry, the other way around, a level platform underneath it. So I put the level platform underneath it, but it's not the same refrigerator. So that's where tipping point came from, is that once the refrigerator tipped over, going back to the level platform is not enough to restore system function. In order to get this thing back upright, I now have to take my parameter, which is my angle, and move it all the way the different direction. I need to now have the refrigerator sitting on this much of an angle so it'll flip back into its original position. And then I can start using it as a refrigerator again. I have to wait like 24 hours because of the coolant and all that, but putting all that behind us, but like the idea here is that this tipping point there, that's where, you can put a refrigerator on an angle, but you got to be careful because if you put it close to that angle, the slight perturbation will cause you to go from refrigerator to no refrigerator, and it's going to take a completely different angle to get back. Now that's for a reversible transition. There are systems where once you've tipped, there's no way to go back. And that's where the physicists got this idea of tipping point from thinking about wine glasses. If you have a glass full of wine, it's got the same tipping point. But when you tip that wine glass over, it might be possible to right the wine glass, but the wine ain't going back in it. The wine is spilled. It's done. And so tipping points are often associated with irreversibility. And so we see lots of examples of that. Let's say in the climate systems, there are a bunch of these systems here where if we think about temperature, some of them we think are close to reaching tipping points, other ones have reached them. And there's just no way, like, let's say you melt all the Arctic sea ice. If you somehow could engineer the world to come back to a normal temperature again, it's not going to refreeze the ice in all the same places. So like, you're not going to get the Arctic sea ice back. So that's an example where if you melt all the ice, you're probably not ever going to see the same planet again, even if you can get things, even if you could freeze the planet again to get some ice back, the ice is going to come back in different spots. So that's an example of an irreversible tipping point. But I don't want to so we're going to end here in a second here, but I don't want to end on a bad note. So there are tipping points for climate change, and those are scary. There are also interesting tipping points for political instability. It can be scary, can not be scary. And so the idea here is if you start, there's a certain amount of tolerance that people have in a population that like they'll tolerate bad government for a certain amount of time, but eventually you go so far, they rebel. Now, at that point, once the rebellion has started, you can't go back to the old ways. Okay, sorry, too high taxes. I'll go back to low taxes. Everybody's fine, right? Once the rebellion started, it's kind of, the horse has left mixing metaphors here, but the horse is out of the gate. There's no putting it back at that point. Attitudes and social norms. These can be good tipping points. You might advertise enough to get people to start recycling. Once they start recycling, when you can back off advertising, and they might stay recycling. And so that's an example of a good tipping point where it takes a little bit of effort to shift the system into a new mode, and then you can back off and it stays in that new mode. So that's kind of an example of a good tipping point. And so these are really interesting dynamically. Why, like, Malcolm Gladwell makes a ton of money off books that he sells about them, and we hear about tipping points, but very often people use tipping point in the wrong way. It's a really nuanced thing about parameters that if you push a system too far, it changes the system. It's not just it moves the system around, it actually changes the dynamics of the system. That's kind of the tipping point here. So I was, if I had a few more time, there's a few more notes I'm going to say about the chapter, but the really big thing I wanted to take away from this chapter is this idea of tipping points. So are there any questions about that before I let you go? I do want to quickly note that that's something that we didn't cover here, but I think is a really important lesson, is in that chapter. So far, the number of ships has been an exogenous variable. But what I like about this chapter, and something you can think about for your final projects, is by adding regulatory processes, they've actually added into the dynamics the psychology of how you choose the number of ships. So the system chooses its ships for you. And that's endogenizing an exogenous variable. And that's a good message for practical things to do. All right, so with that, I don't want to keep you too long. And so I'll put into the chat here the links. So the question that I'll have for you is, what is the name of the diagram that relates parameter values that summarizes the long-term behavior of a system for a wide range of parameter values? So what is that diagram that we use that puts a parameter value on one axis and the long-term equilibria on the other axis? What is that diagram called? I'm trying to put that in the chat, but ever since a recent Zoom update, the chat is super slow to respond. So those online, if you can't get this link, you'll just have to take it off of the slide, which is also now super slow. There's the slide. The question was, what is the name of the diagram relating parameter values and long-term system behavior? And that's all I've got for you. So that's all I've got. So hope you have a good weekend and good luck with things. I'm sure I think there's a muddiest point due Sunday. Keep working on your projects. Not that many more lectures left. So. Any other questions online? All right. In that case, have a good weekend.